Now, one of the weirdest things that astronomers have found in the last 20, 30 years is this concept, the concept of an accelerating universe. One of my favorite current living physicists is this gentleman, Alan Guth from MIT. Alan Guth is, yeah, one of my heroes. He's just pretty fabulous. He found out that the universe is not just expanding, its rate of expansion is actually accelerating, meaning it's speeding up. Here's what we found. If you take the distance to different galaxies and you can figure out their velocity, how fast they're moving away from us, if we have a steady, flat universe that everything is working just like clockwork, it's going to have a curve something like that. But what Alan Guth and his colleagues have discovered is that in the recent past, in about the last 5 billion years or so, the rate of expansion started to actually speed up. So instead of slowing down, it's speeding up. What the hey? What the heck is causing the universe to speed up? And that is a massive question for physics right now. This concept is called a cosmic jerk. The rate at which acceleration changes is called a jerk. It's an engineering term. And if you go back to the Big Bang, there was an area of a time period of rapid expansion, really close to the moment of the Big Bang. And then it accelerated at the universe expanded at a nice, steady rate. Well, then about 5 billion years ago, it changed from this steady rate of expansion into an accelerated format. It sped up. It's kind of like having a car on cruise control, and after driving 500 miles on cruise control, all of a sudden the car, all by itself, instead of going 75 miles an hour, the car speeds up and starts going 90 miles an hour. And you're sitting there going, what the hey? I didn't do anything. I didn't touch the pedals. Why is the car speeding up on its own? That's the kind of confusion scientists are dealing with. The best explanation for this that we have at the moment is something called the cosmological constant. Back to our dear old friend Albert Einstein. When he was working on general relativity, and general relativity is where he explained all of this stuff about curvature of space-time and things like that. In order to deal with the fact that Hubble saw that the universe was expanding, Einstein wanted to make sure that his equations for general relativity actually matched Hubble's observations, because we want scientific theory and scientific observations to match. So what Einstein did, he added a cosmological constant, kind of a mathematical fudge factor, into his equations for general relativity. Now he did that to make sure that the laws, the rules of relativity matched observations, but no one, including Einstein, was comfortable with this. It felt awkward, it felt weird, it didn't really match all the observations at the time, and one of the things that this cosmological constant did was it predicted acceleration. It predicted we'd get to a point where the universe is going to start to accelerate. And later, Einstein actually took this out of his equations because he was so uncomfortable with it. Those of you who are truly nerdy, here's one version of Einstein's equations for general relativity. This is lambda, capital lambda, and lambda is the symbol that's used for the cosmological constant. But go back to the 1920s, everybody thought the universe was flat or static. It was expanding at a steady rate. And this cosmological constant kind of acted as an anti-gravity to keep the rate of expansion steady. And Einstein threw it in there, and remember, he was not totally happy with this concept. So What he did was he later removed this value, and he removed this value from his equations for general relativity. Now, some people are quoted to say, and some people say Einstein even said, that this was the biggest blunder of his life, because with his cosmologic constant in his equations, he was foreshadowing the discovery of what we today call dark energy. The math is the tool of science. Math is the tool of astronomy. And the math said this stuff would be found. But all of the very bright, brilliant people at the time said, that's nutty. We're not going to find dark energy out there. And so they took it out. Einstein himself, the great scientist, took the lambda constant out. Today, what we're doing is we're debating the value of lambda. What is the value of that cosmologic constant? So what that cosmologic constant did is it gave the vacuum of space energy. Why does it have the vacuum of space? Due to things that are called virtual particles. Now, virtual particles are particles that are created out of pure energy. This is a lovely, different little video of space-time foam. And space-time foam means that you can have just energy. Think of it as just heat, just light, and out of it, matter. So energy over here, out of that, little particles of matter can be created. And those little particles of matter can be destroyed and enter back into the puddle of energy, and can come out and form little particles of matter and back again. This is a nice little video that helps explain and illustrate this very unusual and nifty thing called space-time foam. So I'm going to ask you to watch that video next, and then we're going to have a discussion about dark energy.